So, good afternoon, everyone. I would like to thank Rituraj sir for inviting me as a speaker to this event. My talk will be based on like 2 days. Firstly, today it will be a step-by-step software demonstration on numerical, along with a demonstration for example of an optical ring resonator simulation and the result analysis. And the second day I'll conduct on Saturday. It will be in the first half, which I will explain the simulation of an optical grating coupler and an electro-optic modulator. Uh, so this is the agenda which we have planned out for day one and two. Firstly, today I'll describe like why the essence of numerical, how does the software work, and what are the different functionalities that it offers, and why it should be used across the photonics community and how it implements in different applications. After this, I'll gently discuss the principle of FDDD and the mesh solving algorithms, how it gets implemented with the nanoparticles or the nanostructures, how the EM boundary conditions and the Maxwell equations affect the nanoparticles. After this is done, we will move to the numerical software and simulate an example of an optical ring resonator. For the day two, as we have already covered the different solvers for numerical, we would use the different solvers like the mode, FD, and the heat and charge devices to get our data and include those electro-optic data and simulate our structures. So starting with the first thing, like the ANSYS numerical software, it is a multi-physics simulation software which provides a diverse background and gives us various facilities for designing photonic devices and circuits. The first three software solvers are the FTDD, stack, and the RCWA, which gives us an essence as how to design the nanophotonic particle designs. These three solvers operate on the FTDD regime, and will after I'll just give an overview of how to like what each of the solvers propose, and after that overview is done, we will go dive deep through it and see the different uh, uh, like functions which each of the uh, these solvers offer. Now, secondly, this numerical offers an FD, the finite difference eigenmode solver, along with the EME, which is the finite difference eigenmode expansion solver, and the VAR FDTD, which is the 2.5D variational FDTD solver. So there might be a confusion that why the existence of VAR FDTD and along with FDTD. So FDTD is a 3D solver, whereas the bar FTDD, it like collapses the 3D into 2D and helps the simulation time and the meshing accuracy by like it reduces the simulation time.
Ate school
Yeah,
ana
hata boarding sijawahi ku interested
day school ana shida. Lakini watu wa day school ni kama kwangi.
Uh, okay, after the VAR FTDD, it offers for multi-physics photonics design device which offers the charge, the DGTD, FEEM, heat, and MQW. So what are these? The charge offers the 3D charge transport solver, and the heat gives the 3D heat transport solver. The charge we will use on the day two, as we can solve the electro-optic modulator through this device, and heat we use when we require the thermo-optic devices, right? And DGTD is also used for plasmonic based simulations, while the FEM can be used for the different optical fibers like the hollow core fibers and different solvers, while the MQW is used for the quantum wheel gain solver. Apart from this, when the device is ready from our side, we can also integrate it on a system level, which Lumerical offers, such as the interconnect solution. What does the interconnect solution offers? Basically, it is a photonic integrated circuit solver. All the built-in modules are there, and if we want to create or build any like suppose a waveguide with a different like effective index or the group velocity, or suppose we want to build a like electro-optic modulator with our own doping levels and those things, then we can build it separately in the multiphysics device and the FTDD, and then we can import it into the interconnect to see the effect on a whole system level. Then it offers a Q interconnect, which recently also gives us a quantum photonic circuit solver, along with a CML compiler, which is a photonic model development platform. So the CML compiler offers the PDKs from different foundries. It offers from AMF and the Photonics, and they offer different PDKs which we can implement, like import it into our circuits and build our system level designs. Lumerical also offers a numerical scripting such as the Python or the MATLAB API. Along with that, on the system level, Lumerical is integrated with Cadence Virtuoso for the EPDA, such as the electronic photonic design automations, and the K layout for making the mask layout structures for tape out purposes. So if we want to make a user interface device in the Lumerical and import it into a K layout, we could do it via with the interface between the Lumerical and the K layout. So starting with the FTDD solutions, so what does it offer? It basically is an integrated design environment which offers the built-in object library. So in the library, there are already many built-in objects which we can modify, but those modifications cannot be done manually as those objects are built through scripting language. So we have to alter the scripts and see those parameters, how they are functioning with the devices, and then we could alter those. While we can also import the GDS files or the image or the STL. This FDDD solution offers an essential and or rather an interesting thing, that if we have a SEM image or a litho image or an AFM image of a nanostructure, like suppose we have fabricated first and did the study, we could import that same image into our numerical FTD solver and create the structure. The solver will itself create the device through that same image, and we could simulate that to see how the imperfections which have been involved in the fabrication could be solved in the simulation. Basically, sometimes it might be difficult to implement those imperfections manually. So this feature gives us an upper hand on how to do that. Secondly, comes the materials. It has a built-in material library, okay, which supports many material types, including the nonlinear or fully anisotropic materials, along with the multi-coefficient models. So if we want to include, it also offers to include different type of materials with the NK data or the uh, or different doping data and all will show in meanwhile. After that, it gives us the post processing. It gives us the built-in analysis group library and the integrated script environment. With that, offering the optimization, which gives us an optimization routines of various kinds. So this is the object library which we were talking about. Like if we include the structures and categories, under the categories, it has been distinct into different parts like the cylinders, cylindrical fibers, or the integrated optics, photonic crystals. So along in this, we can select the one which we want to work with or which is the closest, which represents the structure we have in mind, and then we can alter it according to our need. Secondly, how to import the things. It imports from CSV files, it imports from image, it binary imports, and it also imports the NK data of materials. Like if we have done the ellipsometry of certain material and we want to import the NK data of that material, it could be included in that way. Or the STL, which is the stereolithography process. If we do the lithography process in different CAD, like 3D CAD modeling, if we do, and also if we do in the mental graphics, if we do the litho process and we want to import that structure into our design, we could do it through the STL. The surface is, we could design a surface of our own, or we could include it from CAD, 3D CAD libraries or AutoCAD pages. And after the GDS files, it all we can also import. Like Lumerical also offers exporting the design directly to K layout, while it also offers to import the GDS files. Okay. The materials, it offers a wide range of materials, which gives us, suppose the name is given here, and the mesh order, the color, the type. So color can be altered, and the mesh order can also be altered. The mesh, the part of the mesh we'll discuss meanwhile in the following slides. The mesh plays an important role in this solvers. So the different material data types which are included in the numerical software are these: the NK material or the analytic material, Chi2, Chi3 Raman car, Chi3 or Chi2, the conductive 2D, conductive 3D, the current driven gain. Under all these categories, we could include our data as per our requirement. The Salmar equation and the graphene or the fold level 2 electron, or the sampled 2D data or sampled 3D data. For the for the we use basically the sample 3D data or sample 2D data primarily, and according to the applications or our need with changes, we change our input source. Uh, After include selecting the material, it is important to do the multi-coefficient model of the material. So what is the essence of this multi-coefficient model? Like why should we do it? So it basically runs an algorithm to match it with the FTDD model. The material which we have included, does it in the vacuum, does after the Maxwell equations uh, have altered it, does it give the proper NNK data or not? The real index and the imaginary index. Even if, and the here are the RMS errors which comes into the account. Suppose if we are doing a simulation and the solutions are being given as diverging. So those diverging problems are mainly occurring through this. So through this material explorer. If the material is not supported, then it might be difficult. Like it might cause a problem due to that, and the results might vary. So the RMS error, the lower the RMS error, the better is the matching of these material coefficient model. So the post processing part is that So in the object library, as we have shown you the structure part, the different imported structures are already present. There is a category like analysis, where already we uh, pre-process the scripts are written for analyzing the data, such as the advanced analysis, the band structures for the photonic crystal uh, circuits and the fibers. For the optical power, we can get the far field. For the resonators and modal analysis, the Q factors are already there. So we could include those to get our desired data. The scripting makes our life pretty simple and automated. Although we can do manually, but when we are there is a stack of materials or a uh, large area device, altering each parameter is very difficult. So we are like each parameter, if it depends upon another, to pose very difficulties in doing it manually. So it offers a scripting language which is quite similar to the Python language or the MATLAB language. Basically, along with that, it's basically calling. Firstly, if we built an object manually, the parameters which are there in that object, we have to call that object here, so that we could uh, alter those directly from the scripting. So it's pretty easy, as I will show you that also. The optimization part. So optimization of different parameters here proposes on different algorithms such as the particle swarm optimizations with the pure generation sizes and the maximum generation. This also gives us an optimum figure of merit upon which the device may be working uh, great. I'll show this part will come into the picture on the second day. Then I'll show you the grating couplers and how to optimize the pitch size and the fiber placement with the angle. Okay. So the FTD offers a wide range of applications such as the 2D, 3D Maxwell solver for light propagation. The 2D one is the 2.5 var FTDD, and the 3D is the FDTD Maxwell solver for light propagation. It can handle any geometry and material and the sources, while it is used when the feature size is of the order of the wavelength. So when the feature size gets around the wavelength of the source which you are shining upon, the FTAD works most efficiently. The accuracy method can be optimized by using the finite size mesh or the finite size time step. So time step functions or the step meshing is the most essential part here, because when the gapping between the nanostructures gets smaller, the Maxwell equations behave differently there. So a higher mesh will be essential in that part. It gives us a single simulation which gives us in broadband results. Previously, uh, before 2015, we have to if we wanted to do broadband simulations in suppose plasmonics or in other, we had to do stepwise in each lambda, and then stitch it to get a broadband. But now it offers a single simulation giving us a broadband result. It also supports simulations on the GPU and CPU, and as well scales with the parallelization. We can also, if the simulation time is huge, we could also cluster with different computers and get their IP here, so that all four gets connected, and each if we give optimization of 10 parameters, it might get divided and connect 5 IP addresses. It might get distributed in two among the five, which reduces the time hugely. Right. So the applications mainly are the metamaterials, plasmonics, the gratings, solar cells, CMOS image sensors, the LEDs, the liquid crystals, and the nonlinear optics. So after FTDT, there is another solver, namely STAC. So STAC is basically an analytical method to determine the optical response of a multi-layer stack. It is mainly a script-based function because it is quite difficult to alter manually the different layers, right? How to control the manually alter it.
ਇਹਨੇ ਬਰਾਬਰ ਦੇ
ਹਾਂਜੀ ਸਰ
ਤੇ ਤਿੰਨਾਂ ਦੀ ਬਾਕੀਆਂ ਦੀ ਫੀਸ ਤੇ ਹੋ ਗਈ
ਉਹ ਸਰ ਦਿੱਤੀ ਹੈ ਸਰ
ਸਿਰਫ ਤੇਰੀ ਦਿੰਦੀ
ਜੀ
ਹੈ
ਸਰ
ਕੀ ਨਾਮ
Okay. So stack is mainly for the plane wave illumination. So in plane wave illumination, the transmitted and the reflected part, study the transmitted and the reflected power, the complex reflection and the transmission coefficients, and the field information upon which it is being studied. Along with that, it is also used for the dipole emission, such as the luminescence and the radiance as a function of the emission angle, along with the percent factor and the far field emission power density. So the stack is mainly used for multi-layered structures, which makes the study easier in this solver. Like moving after this is the RCWA. RCWA is mainly the rigorous coupled wave analysis. Uh, so this is used mainly for the semi-analytical method to simulate multi-layer stack with periodic gratings, and it is much faster than the FDTD in most cases. I would like to mention a point that FDTD is the most generalized solver among all the solvers here, so it takes into account every aspect. Suppose the mesh size, suppose the simulation time, and temperatures, and if we do the override meshes, which I'll also mention. So if we want to simulate a final final device with all the parameters optimized, then we should go to FTDD at last, as it takes huge time, but it gives the most accurate results. And if we want to do the optimization of the, like suppose changing the group velocity or the coupling length for the ring resonators, these small simulations should be done in mode solvers, suppose such as the EME, FDE, FEEM, these things. So this takes few seconds or 1 to 2 minutes. So as we get to know how the parameters are operating with each different variables, then we could finalize those and bring our simulation to FTT. Okay, so continuing with the RCWA, it is basically faster than FTDD in most the cases, and it's pretty simple to set up. RCWA also directly exports the files which are used in the Zemax Optics Studio. I have a slide showing the how it is being getting interfaced to the Zemax Optics Studio. These are mainly used for the AR VR purposes for the meta lenses. It shows you a virtual view of the real world, showcasing that how the devices on the nanoscale or the microscale which you have made operating in the real world. So it is directly an interface with the Zemax Optics Studio, which gives an upper hand in today's world. So moving on to the mode solver. After this FDD solver is done, we move on to the mode solver. In mode solver, there are solvers such as the FD. In FD, the mode analysis of the straight and bent waveguides with uniform cross section and waveguides with helical cross section are measured. So this study is done on the parameters. What parameters? Such as the mode profiles, the effective indices, the loss or bent loss, and the effective area, along with optimizing the power coupling between the modes. So basically, if we directional couplers, we could optimize the power coupling here, and also the frequency sweep for dispersion and group index. As I was mentioning, that if you or if anyone does the simulation directly in FTDD and try to change it manually, all the parameters and study it, it takes a lot of time. So basically, the flow should be optimizing small parts in FD. These simulations hardly take 1 or 2 minutes, and after that, as the parameters get finalized, we could move on to FTDD. In FTDD, as the wavelength, as the mesh size gets decreased, it could take a huge time to approx like basically what it could take a 1 day also. We doing the mesh analysis part, right? So after the FD, we have the VAR FTTD, which is the 2.5D variational FTTD. It is suitable for the large planar photonic devices as it collapses the 3D device into 2D, and it is ideal for the initial designs to check out how the device is working out and to have a process flow. While in EME it is an eigenmode expansion solver and it is suitable for waveguides with non-uniform cross-section and bidirectional propagation in the long waveguides. It also has a built-in propagation sweep tool which allows length sweeping. So suppose if in other solvers you had to like sweep it manually or through optimization in parameters, it would give the parameters of getting it done between suppose 1 to 5 micrometer. But here in eigenmode expand like and it would take there around like 10 to 20 minutes. But here in EME, if we give the propagation sweep tool, which allows for length sweeping, it would hardly take 1 to 2 minutes. This solver is mainly made for that. Like each solver has its credit and discredit, and we have to know that which solver will be best for our application. So as the device part gets over, sorry, as the nanophotonic part gets over, we are moving on to the device part. So device part consists of what? It is basically a finite element based solver, right? And it gets the integrated design environment, importing the GDS, STL, and image also. It gives the comprehensive material models along with the multi-coefficient model for optical materials. In post-processing, these gives an integrated scripting environment which is same as those, and optimization also it has the built-in optimization routines. What is the charge transport solver? So it is basically a electrical analysis of the semiconductor devices. It gives us the steady state, small signal AC, and the transient simulations, along with the supports three material types, suppose the insulators, semiconductors, and conductors. Also giving isothermal, non-isothermal, and coupled modes. It includes the coupled charge and multi-quantum wave simulations. These applications revolve around the planar silicon solar cells, the photodetectors, and the electro-optic phase modulators, the gas electro-absorption modulators. Right. Basically, we can study the steady state of small signal AC and the transient simulations here, and export the file, the .dat file, and import it to the in the FTDD to study how the electro-optics parameters are altering and affecting our optical parameters here. Right. The multi-quantum well solver gives us the 1D physics-based solver for calculating the optical and electronic properties of the multi-quantum well stacks. The MQW solver returns the following results, such as the gain and spontaneous emission coefficients, the complex refractive index of the MPU, the electronic band diagrams, band structures, and the wave functions, the exciton energies, and the wave functions. So it also gives the multi-quantum well edge emitting lasers. Right. These are the applications of this solver. The DGTD stands for the discontinuous Galerkin time domain solver. It is also a type of FDTD solver, but the algorithm upon which it works is quite different. It solves the Maxwell equations in the time domain, but it uses unstructured mesh and can accurately model curved geometries. In FDTD, it gives, like, although we can control in that FDTD to alter with non-uniform meshes, but if we do that, might take a huge time. Whereas in DGTD, if we want to do in curved surfaces or curved geometries, or as it is already built in for this purpose only, it takes a less time. Very much. So the solver also expands the electric and the magnetic field into polynomials up to a user specified order. Okay, along with the sources and monitors that can be directly assigned to the geometric objects. They're effective when having discontinuous fields at interfaces such as metamaterials and plasmonic structures. So these two type of structures are mainly mainly can be simulated in DGTD, which gives an upper hand from other solvers. It also gives the optical and thermal simulations along with the optical and electrical simulations. Now, the finite element eigenmode solver. So these solves the Maxwell's equations in finite element grids. It gives us accurately resolves the complex and curved geometries. So Lumerical is not only software which offers only FDTD. It was offering until one point of time. It was mainly for FDTD, but it has also included the FEM into it. And it also expands the electric field into polynomials up to a user specified order. It helps in the mode analysis of straight and bent waveguides. It gives an integrated workflow for multiphysics simulation. As we can see, the passive waveguides such as the optical fibers and waveguides and active waveguides such as electro-optic phase modulators, thermally tuned waveguide can also be simulated in the principle of finite element eigenmodes. So this offers two type of uh, uh, algorithms. So according to the user, they can use any one of them as they wish. Now coming to the heat transport solver. So this solver solves the heat transport equation independently or coupled with the electric current equation, Ohm's law, in the finite grid elements. It handles optically and electrically generated heat and supports the solids as well as the fluids. Heat solver modes include the steady state, the transient state, and the thermal and conductive. So as you can see here, the thermally tuned waveguide sensor, which is kept here, thermal switch, the metamaterial microbolometer, which includes the heat solver here. Right. So these are the applications which includes this type of solver. As we have covered all the solvers of the numerical on a device level, we now come onto the system level. Like suppose we have made our device as per our need, then how to integrate it into a circuit. Right? For that purpose, interconnect service serves its way as the photonic integrated circuit solver. It gives us the schematic circuit editor, giving both the frequency and time domain simulations. It gives the bidirectional multimode circuit topologies, built-in element library, the foundry-specific PDK elements. It also integrates the CML, as I told, which includes the PDK elements which can be directly included here. It offers the design, simulation, and analysis of PIC, such as the integrated circuits, silicon photonic components, and the optical interconnects. It gives us the parametric sweep and optimization tools and the interoperability with numerical TCAD tools and the third-party tools. Right. So the photonic integrated circuit solver offers, as I told you, the elements here gives us, like, these are all built-in elements, right? As I told, the analyzers, sequence generators, pulse generators, sources, modulators. In design kits, we get the PDKs here. And in custom, we could do it customly, or we could include any waveguides or modulators, and in that file, we could include the exported file from our FTDD or device and include it here to get that uh, principle working in the circuit of our own. And so with this, we have all this networking, coding, the photo detectors, the receivers, polarization and filters, amplifiers. These are all built in. So this through this we could also do the schematic and see that how the Mach-Zehnder modulators, the ring modulators, optical filters, optical transceivers, the wavelength division multiplexing circuits, the optical switches such as the reconfigurable meshes, which are 16 into 16 or 4 into 4, whatever as per one's need. It can be solved in these circuits. After the interconnect, there is a part is Q interconnect, which is the quantum PIC solver. It calculates the evolution of a quantum state in a PIC, a Python model that can also be called from within the interconnect scripting. It has the applications such as the nonlinear sine gate, the spontaneous parametric down conversion photon source, the spontaneous four-wave mixing microring resonator photon source. So if we want to do it on a quantum level or nonlinear and include it, we could do this through this sum. The CML compiler. So what it is? So it bridges the gap between the experimental data, simulation data, and the statistical data, and the interconnect. Right. So it automates generation of compact model libraries by compiling model data into the photonic models. So if we want to have the experimental data which we are studying in our simulation and the statistical data, we could do it in the CML compiler and do it in interconnects such as compact models, in virtuoso symbols. Suppose in EPD, it has an interface with the cadence virtuoso for the EPDA part. So we could integrate it into the cadence and do our electronic photonic design automation there. It also has the photonic Verilog A models in Virtuoso. Okay, so we could have our built-in compact library. Lastly, it gives us the Python or MATLAB APIs. The Python or MATLAB APIs are having the automate complex workflows or optimizations, analyze data and produce publication quality plots. Along with it has been included the inverse design optimization techniques, which has been included in the PIC recently. So through inverse design automation, we could configure our PIC through MATLAB or the Python scripts. So developing scripts or programs that treat numerical solvers as client or in high performance computing settings, the performance and license utilization are necessary. So it also offers high performance computing with the numerical as well as running multiple simulations in parallel, such as the sweeps and optimization. We could also configure other IP addresses of computers to run it parallelly there. It also distributed computing running a single simulation spread across multiple nodes, which I mentioned just now. It also increases the speed of our workflows. It can like recently they have also included the Microsoft Azure part for cloud computing and the Amazon Web Services were previously there with the Ansys Cloud Direct and Ansys Gateway powered by AWS. So this is the system suite for the PIC simulation. Basically, we could do on our own the device part in FTDD modes and charge heat solvers. Then do it in the numerical interconnect that we could see the frequency and the time domain simulations, the eye diagrams, the corner analysis, how they are working, and the Monte Carlo analysis. And then we could take our take our files into the Cadence Virtuoso to see how they are working with the EPD electronic photonic design part, right? To have the proper ideas of how the eye diagrams are taking place and how with variability and non-variability the PAM4 or the 16 cam for signal communication and these parts are happening. Now the interoperability from micro to macro scale. So this part, as I was mentioning, the Zmax Studio part, where so the RCWA we could make those structures, right, and then include it in the ANSYS Zmax Optics Studio, which gives us the lens system, right, and the lens system. See the grading data profile step 2, the ANSYS numerical takes into account for grating design for diffractive optical elements. And then in step 3, the ANSYS COs comes into the picture. This is the process flow which is being followed here, right? Similarly, in CMOS sensor camera, the ANSYS Zmax Studio comes into step 1 for optical design of lens system. Then the ANSYS COs comes into the picture for the exposure mapping and how real life problem it is being taken into part. Then after this, we are doing the ANSYS numerical for the CMOS image sensor for calculating the internal quantum efficiency and the internal external quantum efficiency. After one that is done, we get this pure sensor system exporter for electronic mapping the real world. Suppose this gets mapped here, and how it is getting mapped, how it is getting the heat exposure of the person there for sensing. This that comes into the picture. Similarly, for the exit pupil expander with 1D or 2D grating, we get here such as such as the ANSYS numerical for constructing parametric grating models, and then the Zmax Optics Studio, such as building ray tracing system and measure power at the pupil, okay, for the irradiance map at exit, and along with the Zmax Optics Studio plus numerical, which gives us the built image sensor and the eye models, which are generally received by the eye. And after that, it directly does the Zmax Optics Studio and the numerical, which set up a variable and merit function and optimize it for more for like how it is exiting from the pupil, how the image is being formed for this purpose. Meta lenses have also been included in the numerical uh, functions, such as the ANSYS Optics Studio takes part of the analytical formula optimizations. The ANSYS RCWA gets the radius and heights of how while the ANSYS FTTD simulates the entire lens and reconstruct the field for lens while using the fields from unit cells. Okay, so it actually simulates the near and far field for the lens. After it, in step 4, we give the ANSYS Optic Studio, where we import the near field and propagate for optimizing the system response. And after that, in ANSYS FTDD, we import the phase map for lens for the GDS export of the meta lens, such that we could fabricate those. So this is the flow of the ANSYS numerical and the various solvers and applications which it offers. So like I like for the ANSYS numerical part, an overview has been finished. I would like to take a like 5 minutes break and start with the introduction to FTDD. So with introduction to FTDD, I would showcase you that how this rigorous couple the Maxwell equations and the ESL algorithm are working in the real life, and how it is being implemented into the numerical FTTD, so that you will get a clear visualization as how the things are actually operating. Okay. Hello, if anyone has any questions regarding the part up until which we have covered, anyone could ask some questions in the meanwhile.
Hello, thank you so much for your presentation. I have a question. I want to know, is it possible simulating active layers in laser semiconductor with numerical?
Uh, yes, it is actually possible. As I've shown in the active layer, you have to first take the 4 to 2 level electron for importing the material data. I am showing you once. Wait.
Is it possible in a photonic
Yes,
crystal?
yes, it is possible. It is possible. Actually,
Uh,
you
okay.
once.
With which module? FTTT or other?
Yes, yes, uh, for studying the for 4 level to electron, you have to take the material data from here, right? And then if you want to include the for lasing application, right?
Okay.
For
If
for FDDT.
okay, if we want create an active layer with a quantum well, we use we have to use FDDT or quantum well or
No,
quantum.
For that study, we have to use quantum well. For in quantum well also quantum well solver also, the these materials importing part is there. Basically, all the parameters which I have shown this how it gets offered. All these are offered in all the solvers across. So if you have the application of quantum well, then you have to do it in there, or you have to see if you want to see the carrier absorption rate, then you could also see in the charts and include that data file into the quantum well to see how it is getting related to your application.
Thank you so much.
Oh, thank you.
Any other question from participants?
Okay, so I'll be resuming with my presentation. So as we have covered the different solvers of numerical, we'll now be heading on to the introduction to FTDT. So how the FTDT basically works in the photonic devices. The finite difference time domain method is a method for simulating interaction of light with structures and materials. So it is the most widely used and general purpose method, while it also simulates a wide range of phenomena in photonics such as the photonic crystal cavity or the grating coupler or the ring resonator and the metaphor. It generally revolves around basically the Maxwell's equations. So in the absence of the free charges, the electromagnetic phenomena is generally described by these two equations. So the E and the H are the electromagnetic fields from which we can determine our quantities of interest, whereas the eta describes the materials that are arranged in the space, which describe the device which is being simulated, which has its own effect. And along with that, the J describes the electric currents, the moving charges, which injects the light into the system. So all these parameters basically have been subdivided into different solvers such that the computation and the device also works smoothly and the computation time also gets reduced. So the main goal is basically we can look it as a stitching of a different processes altogether. So solving the Maxwell's equation, the goal of FTDT is to solve these equations for electric and the magnetic given the E and the J, right? So if we know those, we just want to see how those electric and the magnetic field are altering. So these are the two equations, and for the given some device which we know, suppose we are seeing how one material, the material behaves if we shine light on it, right? So basically, this is the principle or the idea upon which we are working. So this is the device. We have the ER. We give the FTDT. We keep it into a FTDT solver. We give the source with J, and we see the electric field, and from there we get our quantities of interest, right? So this is the workflow upon which this answer whole FTDD algorithm works and how everything in basically the universe works. For an example, we can show here our goal. We have to compute the electric emanating from the source, right? Here is the source and the electric field. This is what this box basically showcases. It is a small mesh which we will see in the like solver. This is the mesh in which the solver, like different devices are kept, and each cell operates as an individual, and it stitches up into multiple and gives us the summation of the results or the behavior of how the electromagnetic fields are behaving, including the boundary conditions at the interfaces. But in this case, we only have a vacuum, a dipole source pointing in the z direction, and the JRT, which is directly proportional to the cos omega t, whereas the wavelength here is 1 micrometer, right? So if we do the discretization here, suppose this is the whole block, and we have several this type of blocks which makes up these blocks, right? So which constructs us the ESL. This is called the ESL. ESL gives us the electric field goes like along the boundary, and the magnetic field comes out or into the interface. So these are the del X. So del X in the mesh cell also, when we do in the solver, we'll see that we have to give the del X size. So del X size should be generally the lambda which we are shining upon by 20 or by 10, right? But here, as the structure is too small, we give it by 50 to get it more finer, and the study of the smaller nanostructure would be more stressed upon. So this is the general principle upon which these things work. We just discretize it and see each space how it is working, and in that, like, this del x, what is the length, how to calculate it. It will approximately be the light shined upon by 20 or 10. 550 might be too small in some cases, increasing the time too much. Basically, what happens when we decrease this, like increasing the denominator, such as 10, 20, 30, 40, at one point it saturates. So we have to find that saturation point so that our result does not change after that. And at one point that we attain that saturation, we could say that the our system is stable, and however we alter our the devices, the result will be same only upon the parameters which we are changing. Okay, so this is a main part in convergence testing which we'll discuss. Similarly, we give the boundary conditions. So with the computational domain, it surrounds by the PML with a thickness of typically 10 E cells. So the thickness of the PMLs is necessary, as the light should be absorbed sufficiently so that no artificial, like, the boundary should not interfere in the simulation uh, like its own. Suppose they are generating or reflecting back the light and creating artificial discontinuities or artificial numbers which may hamper or give us the wrong result. So these play an important role. So in vacuum, when we shine light, this is the feel, like if we place a monitor like this, we could see it like this, right? In vacuum. Similarly, if we keep a complex structure like this and give the mesh cells, different mesh cells constituting this, we could see how the electric field is behaving across them, right? So this is basically the study of how, if these things gets more closer, we have to increase the denominator by more, such as lambda by 20 is there, we have to do lambda by 40 and see how the saturation point we are getting. And after that, uh, we can stress that this system is now converged and we can move further. Okay, so as our like my presentation is done, I'll move on to the software demonstration. Just so is the software visible? Could anyone confirm once?
Yes. Yes.
Okay, okay, okay. So I'll show you from the start. This is the launcher basically. This is the ANSYS numerical launcher, and this is the solver. In this solver, there are different solvers which we have talked upon. As it is older version of 2021, which might not include certain such as the RCWA or the Q interconnect. Apart from that, the other one are present such as the FTDD stack, FD, EME, RTD, and according to the need, we could work in any one of those. Right? As I have chosen the FDTD here. So this is the FDTD solver. Right? This is how it looks, and this is like if this is the editing property. This part is the duplicating. This is the move. The duplicating can also be done by Control C and Control V. And this is the move, how to move. This is the array with different lattice constants given. It's deleting. This is the pointing objects. If we want to zoom at a certain part or pan accordingly, pan view, we could also measure the distance or the length as per our need. If we want to fit in the whole structure to our extent, if we want to remove the grids or edit how it looks, this is the mesh, how it looks. Right. I will show how the meshes occur here. This is the FTD boundary region. Like every time you do a simulation, uh, including an FTD boundary region is necessary, as it would like direct that this is like in this region only the simulation is occurring. The Maxwell's equations are getting solved. Anything outside the boundary does not be will not be included in the simulation results. So if we show give the mesh, this is how the mesh cells look like. Okay, this is the mesh cells. This is the how it looks like, and each of this, as I've shown in the presentation, works in this way. In each they solve them in patches and they stitch up, giving us the desired result. So, then moving on to here in materials. So in materials, here are the different materials which you could see how to. And if we want to add a material from outside, these are the options where you could suppose in sample 2D here you want to do, and suppose you want to import the real and imaginary part, you could do it from here and select the file. Okay, so select the file, you could do that. Similarly, okay, so similarly any of the under anyone you could add any of the datas which suits up to its need, right? These are the tolerances for suppose AL2O3. The tolerance is this, the maximum coefficient. The wavelength is given here. The real and imaginary indexes are given here. So it ranges from 400 to 1.24 wavelength. So this is how the thing looks in the material. Similarly, in structures, we have these structures such as the triangle, rectangle, polygon, circle, the custom. If we want to do it customly, like including, we want to like have a surface according to an equation of our own. We could include the equation here. Suppose we want to do edit in custom, we have to give the equation here, and the equation microns are here. We want to make it non-symmetric. We have to give another equation here, right? So, so So what basically we have to give in the structures parameters. So basically the x span, these parameters x, y, z. The materials in here materials it is coming here. So you could select any one of them or give the index which you want to do manually directly here. if you want to override and mesh from the material base. Suppose what is the feature of this override mesh? In numerical, there is one thing that you cannot subtract two structures, right? So you can't subtract these two structures. So basically, the smaller the mesh order you give, the higher the importance or it gets from the meshing algorithm. It will mesh that structure first. Okay. So suppose if we keep a circle here, okay. um, and if we give the material as silicon, okay, the mesh uh, here will be suppose 3 I am giving, and we want to make a circle in between. Suppose this will be 0. If we give it as suppose silicon and give a mesh order of 1, right? We give this one, okay, and give a monitor to see how the index is working. If we give or keep it at 0, all. See, now what I have done, this is the silicon structure, the square one, and I want to etch into the silicon structure. Okay, so I have made a different material circle of silicon. Although it gives a function such as directly etch into it, so it will directly etch. But I want to clear my view upon how the mesh order works, so that you could subtract anything uh, according to your own need. So here, this is a different material. So if you want to make a hole in this structure or etch it, so you have to give the part which you want to remove, you have to give a higher mesh order, so that the lower the mesh order, the more importance it gets from the FTD like solver. That this part I have to mesh first, okay, and the other part they will mesh it afterwards. So we get a view like this. This is the refractive index monitor. It basically shows you the refractive index, how these things are working. Okay, this is the part one here, the dark blue. This is the 1.44 or 1 that part. This is the 3.5 this part. So this is how mesh order works. Basically this is okay, did I miss anything? So in rotation, you could rotate along with the first axis, different axis, three axes are there. So along with the axis, suppose here X, Y, Z are here. So along with that, you could rotate it as it requires. Graphical rendering, it basically, if you want in detailed, it will give you detailed, or wireframe if you want to give, it will basically in wireframe like this, they will give, right? If you want the opacity to be low, you could just decrease it, so it will become more prominent, right? So this is the structure part. the attribute part. So how to like as I told you in the charge and heat to do the simulations there and include those files into here. Basically, if you want to do the charge and include it here, you have to include it through the NP density. In NP density, you have to import the data from there. Yeah, I will show this function on the next session as I will be requiring this thing. So you have to include the property from there for seeing how the NP density is working. Similarly, this temperature is of the heat solver, how that heat one is operating. The LC orientation is basically the liquid crystal orientation. The how with liquid crystals as they like if their orientation differs, the proper there is an example in ANSYS application gallery of liquid crystal uh, layer on a ring resonator. It acts as a cladding on a ring resonator. So it all actually shows how that liquid crystal shifts the transmittance graph. Right. After that, the permittivity rotation is there. It is an anisotropic material feature which gives us like if we want to alter the axis, the extraordinary and the ordinary refractive indices. So we could do this through this. And the matrix transform is also a part of that anisotropic material. These are the features in attributes. In components, these are basically all these components are this one. In object library, structures are there and all, right? So if you want cylinders, there are different types of cylinders already present here, right? Cylindrical fibers, if you want black fiber, this core cladding fiber, these are already there. You just have to change the code according to your own need. The ellipsoids are there. Sorry. uh, Dimer spheres are there, coated spheres, ellipses, the extruded polygons, suppose the round corner shape, which are essential in plasmonics, as during fabrication we don't get a sharp ones, we get the rounded corners. So these are very crucial while making those structures. It gives you an upper hand for that. The star polygons, the triangles for tapering structures if you want. There are different ways. These are just one way of doing it. The gratings are there, brag gratings, grating couplers. For the imported objects, as I showed you, the charge to index, that one only is that. The integrated optics is there for the waveguides, directional couplers, linear tapers, ring resonators, combiner, Y splitter. These are all built in. Photonic crystals are there, different, suppose hexagonal lattice. As per one needs, the wood pile one for the 3D. For the 3D photonic crystals, they have the wood pile ones. The polyhedra, similar in the polyhedrons, surface, toroids, or the toroid resonators and all. And this one, I guess, the helix and the spiral. Right. So these are those. And for the analysis, I'm also showing here in the structure column, there is analysis. So here is the advanced analysis under this. We can have this quantum efficiencies where for the photonic crystal fibers or photonic crystals, we could see the band structure or the Bragg rating, we could see how it is operating. For resonators, we could see the Q analysis, the modal area, modal volume. These all have their description here only, what this thing gives, right? And if you want to include this, you have to just press the insert here and it will insert directly, right? So similarly for structure, if you want to insert it here, just give this and do this. So it will directly insert it here, and you can, these are basically scripted, as I can show you here. These are the parameters. I will show you how to do scripting while I do it. This is the parameter script which is being written in the database. So here you have to alter as per your need, and they have called the parameters directly from here. So they have given the variables upon which it can be changed, and these variables are directly linked with the ones which makes this, right? The poles. Poles are generally the vertices. The poles act as those. So these are the one. So our components part is done, and the group part. In group part, we have the container for and the structure group. Structure group is that similarly as I've shown. If we include this, this is a structure group. I'll show you. This is named as a structure group. If you want to include all your different, like suppose here are different things like arc. One second. This is the outer top. This part. This is the outer bottom. This is the inner top, inner bottom. If you do the coupling length to be 0, it will automatically shift it to this. Okay, as these two got disabled, right? So this is the structure group under which different like structures could be included, and the coding part has to be done in the structure groups, scripting part. Similarly for analysis also, in under analysis all the parts are here. Suppose if we want to do the band structure, the under band structure all the parts are here. These are the time monitors which see and plot it out. So under this band structure, all the ones are, and in band structure also it is done through coding. The parameters are here, and the script is here for setup. Variables are here, and for analyzing how to do. Analyzing also they have the way parameters, the results which will be taken up, and the script upon which it has to be run. Okay. So this is uh, so this is the structural analysis, and now the simulation part. Suppose this is the simulation which I showed you. So what does the simulation part consist of? It gives us the dimension. Does it have to be 3D or 2D? If we collapse into 2D, the Z part goes away, right? In photonic crystals, which we generally do in 2D, we have the simulation time, the simulation temperatures. So if you see, suppose the structure is not converging, for converging testing, we have to do it for different simulation time. We have to increase it and see that up to what point the whole of the light in the simulation region is getting out. Not getting out, is getting decayed and going up. Like basically the target is this. And if you want to fill the simulation sorry, simulation area with different material, you could include here, or give your, like if you want to immerse it in a liquid or in an ethanol, you could give it like 1.36 and all. The geometry similarly for x, y, z, right? So here mesh type are different. You have three types of options: the auto non-uniform, the custom non-uniform, and the uniform. In auto non-uniform, the region selects according to its own need, right? But if you do custom non-uniform, you have to give the input here, or you have to, if you want to give it uniform, like the whole should be uniform according to your own need. So dx is that one of del x, the del x by 10 or 20, whichever is required. So this part is that one only, right? So basically our, like if you do the uniform in whole, it will take a huge time. So what, like how the thing works basically, if I want to see, like if we have two nanostructures here, okay, if we have two nanostructures here, suppose, okay, and we have this space, and we know in this space we have to increase the mesh. So why would we like control the whole mesh size in whole of the FTD region? We could only control in this area, right? So it would largely reduce our simulation time. For that part, mesh override is here, comes into the picture. What mesh override does? In the mesh, like in the FTD region, the mesh it gets assigned. Suppose the assigned mesh here is auto non-uniform. But we want to control the mesh uniformity only in this gap. So here you give it the dx, that the structure, like smallest structure, like smallest dimension which you have by 10 or 20. Suppose that you give here in, like in the coordinates along which the dimensions are varying. So like this, you could control and do it efficiently more. Geometry here gets set up if you want, or if you want to give, like based on structure, you can write their name structure circle. So see, in both of the structures, they got assigned automatically. But like if you want the grade to be upon any structure, in that case only. But in the gap there is no name, so you can't give, do this part, right? So in directly defined you have to do. So this is the essence of this one. Similarly, in DT stability factor, this is basically the current number. I'll show you, like there is a book of computational electromagnetics by Tafloff. There it has been discussed in detail how the current number works. So we don't need to like alter anything apart from like just the geometry and this one and the mesh settings here. Okay, the mesh accuracy we have to do for the convergence testing, but until 3 it's okay. After 3 it takes a huge time. There are different algorithms for mesh refinements, okay, but the most commonly used, and unless one is a master in this FTDD computational techniques, we should not alter this refinement algorithms. The conformant variance 0 works for all. Now coming into the picture is the boundary condition. So how to give the boundary condition? There are different options for boundary condition. One is the PML, right? The PML, the perfectly matched layers, which is now generally into the picture. Then is the metal. So see in this part, the metal boundary condition gives done. Then if we have periodic nanostructure, suppose 100 like 10 cross 10, so the simulation time greatly increases, right? So what we could do, we could only give the FTD region on one single nanoparticle and give the like FTD boundary as periodic. So in that they would already know that across this boundary, like the region they have been assigned into, they will calculate that, and they will take into account that around it, across all the rows and columns, that similar condition will be satisfying. So like this, the simulation time largely decreases. The symmetric and non-symmetric, this comes in, I will come into symmetric and non-symmetric at the last. Firstly, we can go on to the block. Generally comes when the source is being given in an angled way, not in a normally, okay, in an angled way. Then we have to give block. Similarly, for the PMC, similarly from the for the PMC also, we need to give it like this. for different in angled conditions. In advanced options, we don't have to like touch any of the ones in this side, right? Not neither this one, but these two. I will tell you what is the function of these two. Whenever you change the, like suppose you are firstly running from 500 to 800 nanometer, okay, and you are seeing you are getting a response. Now you are thinking you will run it from 600 to 1100 nanometer wavelength, but you are seeing the regime between 600 to 800, which is a common one, is getting altered. You are not getting the same result. So why it is changing? It should changing as you are changing the source wavelength, source wavelength regime, and along with that the mesh which gets allocated with that conditions, like the different lambdas is changing, due to which as the mesh is changing, the Maxwell equations are calculating in a different manner. Okay, to solve that problem, you have to give the simulation bandwidth, right? If you are simulating from, suppose your final goal is from 500 to 1500, okay, so give it here from 500 to 1500 nanometer, okay, and also in mesh settings for this override simulation bandwidth, give it here, so that even if you change the source, the FTDD will think that they are in the same, the due to the source they are not changing, as in the FTD regime they have already encountered and solved for the E cell boundaries, that the mesh cell size should be same in this regime, like from 500 to 1500. Okay, so this is the essence of this one, which is quite important. I also didn't know that. I recently studied this one while facing some problems in my simulation. So this is the FTDD part. After that comes the analysis. This is the analysis I discussed. Similarly, here these are the ones. Just for the import part, as I've showed there, we could import the GDS files, the surfaces, the STL, stereolithography, the NK materials, the binary in binary import form, the image forms such as the SEM images or the AFM images from the import from the CSV files. Right. Now the build layer. This layer builder is generally uh, a foundry process. Okay, if you want to make a, suppose a stack, like suppose SOI wafer, then you are giving waveguides, then pastage materials, then metal contacts. Okay, and if you want to and you got that GDS files from a foundry or PDKs, you could just import it here. Okay, and practice it upon that. You can alter the thicknesses here, the pattern materials, the background materials, the processes, the side walls, right? Where is the side? The side wall angles, as during fabrication from 90, it gets altered to suppose like 110 or 105 degrees. So this could be done here. The pattern growth deltas, okay. So the fabrication imperfections could be brought in upon in this one. So this is quite a powerful one. All these things which I am discussing are already there in the Lumerical website. If you will be arising any queries, you could just look into it in that site under different sections. With examples, they have solved it. So you could also see how they are doing it. Right now, we have the sources. In terms of source, we have the different sources such as the dipole, the Gaussian, plane wave source, total field scattered, mode source, the import, and the global properties. So basically, all these can be used according to one's need. Right? You can use a plane wave also. You can use a mode source also. For ring resonator, we can use imports also. No, sir, not import. Sorry. Import is a different. Like if you want to include the a certain lasers properties into your own, which is your own built-in, and it is not functional like already available here, you could import those laser properties into it here. Now coming into the monitors, these monitors have the refractive index monitors. So as we have seen how the refractive index is varying, the field time monitors, it shows the electric field intensities with respect to the time. It has the movie monitors. You can also view like how when the light is moving into and how the electric field scattering, transmission, or the reflection, or the resonating particles are behaving. You could see the frequency domain profile monitor. You can also use the frequency domain field and power. Just the difference between two are that it offers an extra feature of power, and it has a different base upon which the algorithm works. Okay. I haven't shown the sources properties, right? So in mode source, basically, this is how the mode source looks. This is the source direction. If you give the here, so it has the injection axis. The direction it should be forward or backward. If you want to give backward, it will be backward. The amplitude, the phase, and you have to select a mode, right? Here you have to select a mode. I'll show you that how to do that while simulating. You have to select a mode and the number of trial. You can also give them a fundamental mode or fundamental T mode or fundamental TM mode, or use according to your own need. In user select, if you pass on through 10 modes and want to select your mode upon on your own wish, you could select it through this. So if you have a bent waveguide, you could just include the properties here. If you want the source to be in some angled manner, you could include this, right? The geometry is similar for every parameter. The frequency, in the frequency, you could just give the frequency effect, and they will alter it in the terahertz domain. And the pulse lengths. These are the spectrum versus wavelength graphs, the spectrum versus frequency graphs, and the signal versus time graph. Right. If you want to eliminate these discontinuities or optimize for short pulse, these have all their individual features, but for beginners, they are not recommended. As we gradually dive deep into it, we get to know how these things alter what things. So as we get a good grasp into it, we could play with these things. Right. So we can also set the set global. In set global also these functions are already, well, these are only there. So this is the source part, and for the monitors, I could show this that in monitors, if you want to override the global monitors, okay, suppose already in the source it is given the wavelength is this and this kind. If you want, no, I don't want the monitor to see in this or record in this regime. I only want in a small regime, suppose 600 to 700 nanometer. Then you could give in that way. Okay. Or if you want the sample spacing to be in different forms like uniform or custom or Shabby state, then these are all one's own call. Along with that, the frequency points you could also alter. The more frequency points you give, the more detailed or the more studied plots you will get. Suppose in 5 you will get 500. If you give 500, they will give a plot on 500 datas. Right. The geometries are given as this, which are similar to that one. The data to record are this. So no need to alter these data. Sorry, these selection parameters. There's the output power will be same. The px, py, pz. No need to. It's everything is one on one's own need. So they could play around with it to know more. There's no. This is the spectral averaging and apodization part. The partial spectral averaging is there. which gives the delta terahertz part and the time approximation. And in advanced part, these are the spatial interpolation. Or if you want to override the advanced global monitor settings by changing the sampling per cycle, you could do that also, which would directly change the Nyquist limit of the actual sampling. Right. Similarly, in the spatial interpolation, the nearest spell you could specify a specified position or record data in PML. So, but these are generally not told to be played upon because they might alter the working algorithms. Okay, these are already built in as how to. This is the stack part, right? Stack is similarly the layers which will be built upon. So you could just layer thickness materials. So one by one you could just increase. Many features are already there here. Similarly, ports are generally just ports. We could give ports. Ports are generally acts as both sources and monitors, right? In ports, we give this mode 1 and frequency. We give the set global source settings. Like depolarization fractions, the loss, the mode profiles, effective index, source loss, source mode, source and near, this parts, right? So these are the one. And for resources, this is a local host one. If you want to increase your computational capability to the whole system, like if you're if you want to do it through your whole processor, then you have to increase your threads according to the capacity which it can handle. You could just include the design environment. No, you can include the configurations, or you can add here the IPs which I told you that it can be done upon 2 to 3 systems also to decrease the computational time. Right. Now here is the simulation. Check simulation and memory requirements gives us a check that how much memory is required. Is it sufficient memory having or not to consider this? See there, here is the simulation bandwidth which we have set, and the total number of nodes which it has calculated, the RMS error of the different materials which I'll show you just now, and the memory details also, which like each monitor, how much memory are they consuming, right? So it can also be checked from here. Now coming to the material explorer part, suppose silicon is here, right? And the wavelength is here, and we want to see with the wavelength, we can fit and plot here. So we can see that the real epsilon, just a second, with epsilon, if we want to do with the index, we can change it from here and plot it, right? So see, it is perfectly plotting the real. But see in the refractive, imaginary part, there is a minute shift. So we could change this, right? So if the imaginary weight is increased, like the weight upon which the imaginary part is considered, suppose 5, a small maybe output will give us a 10. So like this we have to play around to give the fit tolerance. The RMS error we have to check. The standard RMS error is now 0.08. So maximum coefficient if we give 20, it's not changing much, right? But if we give the imaginary weight as now 20, does it change? See, it has decreased, right? 0.075. Now the stand and the weighted RMS error has also changed to 0.04. So like this, we have to optimize the material also, so that it doesn't include any artificial imperfections into our simulation regime. So this is an important factor in fact. Mm. So now I will mention one thing. Whenever you are starting one is starting a simulation, one should do a convergence testing. So what is the role of convergence testing? So if the system is not stable, it might give you different results for different simulations, right? So we have to first stable our whole environment. So how to stable that whole environment? Suppose you are doing a ring resonator, right? In ring resonator, where we what we look upon the transmittance in the drop port or the through port. Suppose we take one thing, drop port. So we have to see that with each parameter, we are getting the same output. Suppose we have only there is a ring resonator on a silicon substrate, and we are giving a source, and we are getting in the monitor. So what we can see, what we have to alter basically, we should alter firstly the simulation time. Okay, the simulation boundaries, it should be at least at a distance at so not at least at most at a distance of lambda by 2, right? Apart from that, we have to converge it on its own as to see that any light which is getting absorbed by it doesn't get reflected back and induce any artificial imperfections. So the X span, Y span, and the Z span have to be taken into account, right? So we have to check with this also. And apart from that, the source settings we have to see. Like suppose if we change the source position, as we have to just correlate our simulation thing with the real world thing, right? If we change our laser position, our like results will alter, right? If we just move it a little back, little front, our results might shift. So here also the same thing occurs. Okay, suppose if the and for the monitors also, if the monitors are shifted, then these things also like differ. Similarly, like in fabrication for different growth of materials, if we change the substrate holder, okay, so the plumb which forms or the growth of material which forms also gets altered, right? So we have to find a sweet spot in this thing where everything gets stable and there is a perfect simulation regime. So the source position, the monitor position, these two we have to see. Then we have to see the FTTD time, simulation time, and the geometry of X span, Y span, and Z span. Lastly, when everything is done, we can go with the mesh, like at which mesh refinement size it is giving the converged results. Okay, is it in lambda by like lambda by 10 or lambda by 20 or lambda by 25? These are the last steps when we are like going for a like final data for our paper or any project. So with this, and along with that, you can also have this. There are the sources for examples, the documents, the ANSYS Learning Forum. There are different videos or different solvers. You can also go through those. They have a course for different solvers. You could they all have the introductory video for that. You could look into it. The courses also, the ideas, and for any support which you might require, you could do that. Now the optimization part. In optimization, what is there? Suppose here is a new parameter sweep. So in parameter sweep we have done. So we will see what we can like for the number of points. For how many number of points it might do the parameter sweep. So we have to include here the name, the parameter upon which we want to do. The type, is it a number or length or what? The start and the stop part. And in the results part, we have to give upon which we want to study upon the transmittance or the effective index, anything, right? Here, there are different operations for the results, such as the start, the stop, the stop, and the so optimization. There are different algorithms such as the particle swarm algorithm, optimization algorithm, and the user defined. If one has their own algorithm upon which they want to optimize, they can include it here also. So what type of optimization do you want? Is it a maximized optimization or the minimized optimization? You could. Now there is maximum generations and generation size. So whatever number you give here, the total number of times it gets run is the multiplication of these two. Okay. So 15 to 20 is like what 10,000 times. No, 1,000 times. So 1,000 times it gets run. So like this optimization technique takes place. If you want to include some tolerances, you could also include that. And here similar way in the sweep, the addition for different parameters and the figure of merit upon which it has to be optimized. This function, this sweep technique will be used for the grating coupler. So we'll discuss it there also. Okay. Now the Monte Carlo analysis. Monte Carlo analysis also works on the optimization for optimizing purposes. So there are, it's a quite vast technique. Like it has to be studied thoroughly upon for different CML compiler, CML libraries. Okay, to make for different, like suppose you are making uh, 10 like 15 ring resonators on a chip. Okay, and you want to do the analysis of how each placement of the ring resonators are affecting the other. Right. For that, the transmittance is getting off like affected on that. For those purposes, this Monte Carlo analysis plays a very significant role, and it's quite complex also. Now the S parameter. So what does the S parameter do? Basically, if you do a simulation here and gets the S parameter, you could include this S parameter file in the interconnect file, right? And suppose you want to do the ring resonator properties in interconnect, you could include the S parameter files in that. Here are the different in X matrix setup. You get to different define the different uh, setups such as the port 1 and the mode 1, port 1 mode 2, port 2 mode 1, like this. And for the export setup, we we do this thing for different like port locations and this. After this, whenever this part is done, we get to like if we run it, if it is run down, then we get to export it. Okay, if we get exported like directly a option comes like export it to interconnect. We will do this part on the thermo like electro optic modulator. So you will get to know that how to export it to the interconnect. So that part we will discuss there. Right. So with this, I guess I missed one material like boundary condition. Uh, this symmetric and anti-symmetric, right? Just symmetric and anti-symmetric when to use. Just a second. Uh, so this is the symmetric and anti-symmetric boundary conditions in FTD and more. So how, like suppose you have don't consider this like this nanostructures. Consider that a full whole circular nanopillar is there, right? And if you want to do like reduce the simulation time, like in this the simulation time is reduced by 1/4 part, right? One is that the electric components flow in this part for the symmetric boundary, and the for anti-symmetric boundary it gets the green part, right? In similarly in the magnetic components for the symmetric boundary it gets like this, and for the antisymmetric boundary, this gets like, so basically when this antisymmetric and symmetric boundary conditions can be used, it can be used whenever there is a plane of symmetry to the middle of the simulation regime, right? So this some field components must be zero, right, at the plane of symmetry. So that feature this boundary condition takes into the account. So the symmetry boundary conditions are implemented by forcing the appropriate field components to zero, right? And the non-zero field components will be taken into account. So basically, the symmetry rules are always helpful when determining the symmetry of modes found with the mode source and the resonant cavities, right? It actually converts like halfens the simulation regime. Okay, because see, like it acts as, this is not shown correctly actually, this diagram. This, like, if this is the, wait, it's a point, then it acts like this, right? This will be green and this will be blue, right? So electric field in blue regime, electric field flows across like this, and in the magnetic region, like this is the anti-symmetric magnetic, it flows in the opposite. It not goes across the interface, it grows into, as we have shown in the E cell boundary, right? Like E cell is going like like electric field is going like this, and H field is going like this, right? This is the occur. So by this, the simulation regime, like suppose this is a nanopillar symmetry, it gets the simulation time and the space reduced by quarter, right? It gets reduced by quarter. So if only this part is gets simulated, it can stitch up the remaining part. So these things can only be used when we are doing nanohole arrays, or suppose any nanopillars of plasmonic nanostructures or metasurface nanostructures based on their application. So this we have done, right? Now, we will show. Now I will show you how to do the ring resonator part. So this is like, as if I do it in FTDD now, it will take around a long time, like 1 or 2 hours to simulate. So I'll show you like from scratch how to build a ring resonator in VAR FTDD, which is a 2.5 2D simulator, as it compresses from 3D, and you will get the same features here from this VAR FTDD and mode. We select how the coupling length and the effective index or the group delay FSR comes into the picture, and after that is done, we finally put it into the numerical FTDD. I already have optimized like ring resonator in FTDD, which I'll show you at the last, and how it got. But from scratch, I'll show you in VAR FTDD, as it takes a long time. Okay. So firstly, we will take a substrate rectangle. Right. This is the rectangle, and the length 25, 16. As it is a substrate, we'll give it as SiO2. So this is done, right? So now we will take a group, structure group and name it as ring resonator. Right. These are the properties here. This will be the 000 and script. We have to write it here. So how to do the script? First, we will do it as delete all. Then we will do call a rectangular structure. How to do that? That is add rect. These commands are already there on that side, but this is how we call an rectangle or any structure, like add that structure name, right? How to assign the like parameters or the coordinates? Everything which we have to assign, but everything which we have to assign, we have to do it through the command set. Set this, and set this. Okay. So now we just have to call the that those functions which are inside those structures into this set. Suppose the x coordinate, which we give as x. Okay, x coordinate is done. Set I'll give the name for this variable as lx. Now I'll give it as set. Give it as span y span comma. The name is base width. Is now the position y which we have to give. It should be radius plus gap plus base width. Right. Now I will copy the similar. This is the bus waveguide we are giving into the ring resonator. Now we'll copy the similar for the output bus waveguide. So we'll do it as copy. It will be the coordinate will be 0, comma -2. Radius plus gap plus comma 6. Right. So this is the copy part. We'll do copy for the y radius. Expand. We are just calling and assigning it the variables. We'll declare the variables in the properties file. So now we'll give the ring. To include the ring, similarly add ring set Yes. Then we'll give the inner radius. This will be the one. After that, outer radius. This will be now we'll copy for the other part. R is 90 to 70. The X and assign the material to it. So set all in material. Now if we don't get the desired material in the like material library, we could give our own material like material index as our as we want. Okay, so for that only define dielectric. Now it will be index index. Okay, and then now we'll give this height of it. Where 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 height all the scripting part is done. Now we have to assign the variables here, whatever we have done. Right. So firstly, the name similar should be there here, the one which we have, and here we have to give the length, like the variable LC, then gap length 100 nanometer, now radius 2.1, index number, index should be number, so it will be 3.5. Right. Now the material material we have to select. Now we have to give silicon here. Then base width, length, and LS. Then we have to give 25. So all the things are done. Now you can also test here. It will give here if any error comes, they will show you the line number and see where the error is coming, right? So this is done. Apply. Oh, okay. So this will be again 90 to 90 to minus 1 minute. Okay. So now it's done. Right. So the ring is now formed. Now we'll give you the simulation region. This is the eigen mode solver. I'll just save this one first. Okay. So we'll give it as 300 is here. We'll just we through this eigen what we want to do is through eigen mode solver. We just want to see how the mode is flowing through the bus wavelet. So it should be dx. We'll set it as dx, right? Now we'll give it as minus 3.8 position. This is and here it will be 3.6, 4, and 1. Okay. So here we have to change the mesh cells. We have to give it as for y and z by 200 and 100, and press start, I guess. Okay. So this is done. Now this is only for seeing the mode, like suppose the group velocity or the effective. Okay, but if we want to see the transmittance how it is working, we have to set up the var FTDD also. And in this in the mode solver, we will look into it as we enable any one of the solvers, the other solvers get disabled, right? So and for this var FTDD, what is there? You could see here some crosses are there, right? So these are used for the effective index calculation. Right, this one will be placed upon the waveguide, and this will be placed upon any random area other than the waveguide, which calculates the effective index between the two blocks, like the step index, which we could visualize. So here it will be simulation time. 5,000. This will be 10. Apply. Effective index minus 3.1. Lab mode position 0.05. Okay, for variation, and we want to do it for broadband. And we have to change this. These four are the positions of these blue crosses, and this lab mode position is of this green cross. Okay. T1, these values I have already optimized for the results and converged it. So I am using these ones only. Apply. Less things will be like this only. And advanced also we don't have to do. So here we can see the index plot current. So this is basically the one how it should look like. Okay, the mode is looking fine here. Now we'll give what is required, a source. So we'll give a mode source here, right? The mode source will be this will be not worked upon, mainly the geometry, because with the geometry the mode profile will also change. So it will be minus 4.5, 3.6, and so if we now do it in current mode, okay, we have to change the frequency. I was giving the wrong frequency. Apply. Now I guess the mode will come correct. One point five. Close. So I guess one has been not given. Uh, So we can look into it now. So for the eigensolver, we have this solver, right? Here are the modal analysis, which can be taken into account. The wavelength upon which we want to do the modal analysis is here, along with the number of trial modes and search here. And so calculate modes. Okay, I guess the height is long here. Okay, height is long. Yeah, height is here -2. Okay, okay. Uh, Now you could see we are seeing the mode source here, sorry, the mode profile here, and we have the different effective indexes, wavelength, losses, and the group indexes for the polarization fraction also for this. Similarly, as this part is done, we can do the frequency analysis here, and we want to select this frequency here. So we can track the selected mode which is selected, and then do it till 1.6 for detailed dispersion analysis. And we have to do this multiple optimization, save bandwidth settings first. Now we can do the mode, calculate mode. See, it is done so quickly. And in frequency analysis, same thing we have to do. Now the error is not showing the diverging problem which I told. So see now we can see the effective index plot with wavelength, the loss we can see, the gain we can see, the group index. So the group index we could see here. I guess I should do here from 1.5. 1.5 it is done. Now with 1.6 we should do the frequency sweep. Group index you could see here it is coming. So from group index we could calculate the coupling length of this ring resonator, right? These are the mode profiles. If we want to like global decade, suppose we want to select this data and keep it aside, we could select and then run a new design such that the modal overlap, if we want to do a modal overlap of two waveguides and see how the wave is uh, going from one waveguide to another, we could look into it, right? So this is one way for like studying these parameters. Now I'll so this is now okay. Now see, now the mode profile is coming correct, right? This is the mode profile for the fundamental mode. Similarly, we can also user select from here, from select mode, or as this showing, we can also user select it, right? So for now, we'll do it mode, and wavelength is done, geometry is done. So, so this part is done. So sources are done. Now what part is left? This now we have to see the profile, how the profile is being built, right? So for that, just a second. Hello. Sorry for the interruption. So now we'll give the monitor, what the monitor is required here. So for the monitor, frequency domain power monitor, this will basically be the full profile monitor, and override this one. We want to do the center. So we don't want to use the source limits, and this will be only one. So basically, this will be around 1.55, right? 55. Will be 2 z normal, and this will be 20. This will be 12. So this is the mode profile which is being formed. Now we will give the throughput, like what throughput we have to give it. So similarly, throughput, use the source limits of data. This is also correct. Now we can do this part. We want to check it on the bus waveguide on the output on the throughput. So this will be 4.2 and 0.6. So similarly, we can also copy paste and do it drop code. Drop code will be right. So this will be basically at minus and minus apply. So it's done. Now we can save it and run it. So see in 2D domain, 2D it will be running in like 5 seconds. Right, right. So it has run. So we can see the throughput. See, we can see the visualize electric, magnetic, and the power and transmission, far field grades. Okay, okay, got it. I have only chosen this one should be wrong. Ah, so now you can see that as the ring resonator principle, what is there, as the light propagates through it, it resonates through the structure, and then it goes out to the throughput and then goes out to the drop port. See guys, okay. So we can also include the drop port in the same visualizer here. We have to do the absolute here. Okay. So like this, it does in a Fabry-Pérot cavity. Okay. So this is. I want to show you the that FTDT part also, but as we are short in time, I'll show you the ring resonator in FTDD in the next session. Like it's already simulated. I just wanted to show you how the like how it is only similar. Just the time consumption has been very much less, and the FTDD gives you more accurate results compared to the VAR FTDD. But it's almost similar the data with respect to that one. So with this, I will conclude my today's talk in the session one.